Good morning to all of you. We start today. I want to thank the organizer for this very interesting meeting. Our first speaker is Andrea Braides from the University of Rome, Tor Vergata. Please.
Thank you very much. Thanks to the organizers for this very welcome invitation. The iteration of the invitation was there also 2 years and a half ago. And somehow this talk stems from interactions began at the time. So what I'm going to talk about is concerns mathematical modeling and analysis. So it fits in the title, inspired, say, by degradation issues in cultural heritage. So it has no sense of being applied to restoration, but still it's an interesting, me at least, mathematical modeling and analysis problem. So it is related to something, so that should move. Okay. I'm trying to use the arrows here to move the. No. Response. Can you check? This one? Okay.
Okay.
So this picture is taken from the contribution to the lecture notes of previous meeting on the cultural heritage in 2019. This contribution by Matteo Negri about the craquelure. So we're talking about craquelure in paintings, and here there is a painting which we have an unknown author, in which you can see that you have arrays of regular arrays of cracks with some spacing, maybe not so regular, inside of which you can see other kind of networks which are more or less aligned in some direction. So this is a kind of fraction that you can encounter in paintings, in other artifacts like vases or ceramics. You can encounter other types of more disordered cracks, and here is another more complex, more disordered crack that you can picture in another kind of medium, in which you see very little ordering. And this kind of phenomenon can be modeled using two-phase mathematical, two-variable, say, mathematical model, in which you want to picture the surface of an artifact, for example, a painting, and you model the behavior of the painting as a brittle medium deposited or glued to an elastic substrate. So the abstract setting, so mathematical setting, is that you are considering a thin layer of paint, or you can see of glue or another material which sticks to the substrate. The substrate, in the case of painting, is canvas, and what you want to detect is what you want to explain and model is the pattern that you see on the visible surface. on the surface. So what you expect that as you deform the substrate, so this is a mechanism driven by the formation of the substrate. As you deform the substrate, the deformation expands or to the layer, which is brittle, so it may crack, it may displace electrical energy. And what you see then that you localize, so instead of having everywhere a diffuse elastic response, you have a localization of the displacement of failure in some directions, in some zones, and then what you see on the upper surface is an array, is a pattern of cracks. So how to model? So this is the geometrical part, very simple, and how you model then you model the. I see the whole picture here. Please not type. So how you model mathematically, energetically this mechanism? So you have a reference configuration, the canvas, if you want, in which you have a variable which is still an unknown, but is the elastic deformation of substrate. So it's of the canvas. You suppose that you know almost everything how it behaves. So you have a elastic deformation, which you can think of being from R2 to R3, okay? And then elastic energy, which you can think also linear, which depends on the gradient of this deformation. So this is the usual elastic energy, and the variable here is thought to be sufficiently regular. On the visible surface, partially visible surface, you see also a pattern of cracks. So you have a deformation of the surface which allows for discontinuity. So it's a brittle deformation. It's sufficiently smooth outside an array of cracks. Okay, the array of cracks can be thought as the set of discontinuities of this deformation. So that's why we have this S of U here. And the energy is the elastic energy of the surface where it's not broken. And then the simplest way to model the introduction of fracture is by a Griffith criteria. So you the energy that you spend to open a crack is in this two-dimensional case proportional to the length. Proportional with a factor which is called delta, which is the fracture toughness of the surface. And then you have an interaction region. So as in this up until now, you have two unrelated variables. These are related by the fact that you have this thin layer, and you have an interaction terms which depends on the difference, and so on the relative displacement measured on the reference configuration, two-dimensional configuration. And this depends on a small parameter. Parameter which is smaller or larger, say, but we can think of it small, which is the thickness of the layer of the layer of paint. And we think both of these parameters to be small. So you have a small layer painting. You think of classical paintings, not Burri or some other more recent, more concrete concrete painting, say, and you allow for a lot of structure. So delta must be small, otherwise you cannot allow for a number of. So this model had already been studied and analyzed by myself, Andrea Braides, and Sassari, in a completely different context, or inspired by work in a completely different context related to muscles. So it's a biological model in which instead of having a substrate, you have bones. Instead of having, say, a layer, you have sheaves of muscles. Okay, and you sum up these contributions, and our result is some symptotic results, which proves that in the end you have a homogeneous behavior of medium, which is described by a single elastic deformation. So if you have small thickness and small fracture toughness, then in the end something which can be expressed by an asymptotic formula only independence of the underlying deformation. But now, okay, this was a mathematical result, which in a sense proved that you can have a theory in which everything then is hidden in this zero, for which you have a form. Now the input, if you want, of the work of Matteo Negri was to stimulate, say, a better analysis of F0, also in view of the understanding of structure in paintings. So the trivial cases here, which we go very, very fast, are where delta is very, very small. So delta is very small means that you can fracture very easily. And then okay, you have, remember, you have even a part here where you have u minus v. Suppose, for example, that everything is 0 in 0, so you want u minus v wants to be 0, u minus v divided by epsilon wants to be 0. But if epsilon is large with respect to delta, then you can achieve this with a little contribution of stuff. So these parts do not contribute. G can be the deformation then of u is piecewise constant, piecewise constant, and everything is 0. Conversely, if epsilon is, so you have a very small thickness, then there is no fracture at all. Fracture is very rare. So now we want to describe the behavior of F0 in independence of Z and understand how can you interpret this fracture. So if you have so Z is the underlying. So our theorem says that everything can be parameterized in the, on the underlying deformation of the substrate. This is the abstract mathematical result. Now we want to see how this reflects on patterns of cracks. So if Z is small, so if you have a little deformation, then you don't have simply, and this is translated in the fact that all you can take u equals v, and then everything disappears except by the elastic contribution. Now to have a description far from 0, we have to make some assumption, or at least to distinguish cases. So one is the easiest case, or the case in which we can describe rather precisely what happens, is the scalar case. Scalar case meaning that U and V are aligned to some fixed vector. Simplest case is the case in which you have only vertical displacement, so antiplane. So in this case, you have only a scalar variable, or two scalar variables, and you have everything that can be phrased in terms of a scalar product. So the outcome is that remember now we are looking essentially at the profile of the deformation of the upper part, and we want to see the location of the discontinuities. And what we see is that as we deform in this direction, the gradient of deformation here is aligned with the straight line here, the direction of Z, and you have cracks perpendicular to Z, and they are essentially one dimension. So the fracture is localized on lines, and everything can be reduced to a scalar homogenization problem. So the problem here now is to determine the distribution of cracks. So and we see that these cracks are distributed periodically. And this, so this is the cross section of what happens in the orthogonal direction V, and we can so until some threshold, you have no cracks. So if you want the periodicity, the period is infinite, so infinitely apart. Then at some point you start having cracks, and they come with the period lower and lower as the deformation increases. So this is in accordance, if you want, for the first picture in which you see layers of cracks close to the eyes of Mona Lisa, which are aligned to a single direction and they're more or less periodically distributed. And this is not due to a geometrical periodicity. There is no geometrical periodicity like here, but this is just simply energetically driven, and the period depends on the only parameter, which is the modulus of offset. It's important to see that here you have something, some abstraction here, if you want. This plus infinity here, passing from plus infinity to a finite period, is something that you cannot do in a finite sample. In a finite sample, there will be always a gap here, and you start from some fine large but finite. So the title of this talk, or also sorry, of this slide, which you cannot see, is what happens in the vector. So in the scalar case, we are seeing that you have a very regular alignment of cracks. So why we see instead patterns that are complicated? One answer could be the vector. If you have thick layers, then the scalar approximation does not hold, and you have everything which depends on the vector u minus v, and gradient of u and gradient of v are matrices. So what you expect, so you see that patterns, regular patterns, periodic patterns are not minimal. You see, for example, that the arrangement on lattices like these better than lines, and so well, it's a rather complex, and I don't know what conjecture about the minimizer, which should be, in a sense, if everything is isotropic, it should be rotational invariant, and still very complicated, so we don't know exactly how the pattern of cracks will be, but the pattern should be complicated. So this is an answer. Another answer is dynamic. So the complexity can be due to nonlinear evolution. So the fact that you don't have so you have a nonlinear term due to the fracture implies a lot of non-uniqueness, which in cases of iterated minimization problem. So if you model this evolution of these cracks, even if you think that these cracks, the evolution is quasi-static, it is probably driven by some very stressful events, like the variation of temperature and so on. So you cannot expect to have a continuous evolution of cracks, but some events which induce some bifurcation, and so you make some experiments. So the first time, even if you take a very simple sample, the first time you get a regular array of cracks, but then as you evolve, the second critical event, you may have a crack which develops independently on one side. For example, here you can have this crack, cracks which are periodically distributed, and then the next crack can appear here or there with the same probability. So you have multiple events of in which you can choose, or you can have a non-uniqueness. So if you start pulling on one side, you have first a regular array, then you continue pulling, and you have a constraint that the cracks must be contained in the previous set. So energetically, you subdivide some of the cracks. It can be not energetically favorable to subdivide all of the cracks. Then, if the next event is in another direction, then you want to generate cracks in this direction here. If you pull, if the strength is large in this direction, then you can have subdivision which are not regular anymore. So you can repeat this bifurcation in more directions. So this, in a sense, explains that even for very thin layers, so where the scalar approximation is fine or is acceptable, you can have a complex pattern of cracks. And so this somehow is our answer to our curiosity, say, about the application of model to crack lure. I have to say that now, as you proceed, you see the interesting features of this kind of model. We can also proceed in other direction, which are maybe less linked to cultural heritage problems. For example, we can impose a periodicity constraint on the crack. So this can be thought in the sense of cultural heritage problem. Now have a crack lure in mosaics, in which you have a small size of the mosaic, which must be comparable with the thickness here. And here you have a lot of more complexity due to the incommensurability effect, and this becomes mathematically very interesting. So now in these problems, I see that maybe they don't have a direct question on the cultural heritage restoration problems, but still I can see somehow an influence, a suggestion from you can come from these problems and can help us to develop new interesting problems, also mathematics. Somehow there is a two-way interaction in these communities. So thank you for your
And there are some comments. Please.
Thank you. Qua, va bene? Studio televisivo. Grazie per il... Ho due curiosità. Una sull'unicità. C'è unicità qui, anche perché non ho capito se sei rimasto nel caso convesso. Ah, sorry. The curiosity. So one is about the uniqueness, because I don't know if you know the convex case or not.
No,
F and G are convex.
F and convex.
F is convex.
H you can
Okay.
convex or not.
But you have uniqueness of the solution? Because I
No, because you have non-convex part of it. As soon as you fracture, you can.
Because I'm afraid, because if you want to simulate from a numerical point of view, if you try to simulate, if you have enough weakness, probably use some mesh in order to reproduce, you have enough ideal solution. I don't know. There is a problem about if you can prove eventually that you converge to something, but I don't know if that is.
So somehow the depends on the sample, of course.
Yeah.
So if you have very simple samples, then essentially the first step, the onset is unique, but then you have bifurcation. Okay. So if you have a square, you deform on the sides, then the cracks are periodically.
Another minor question is about the boundary condition for the displacements. What is the boundary condition for you?
No, okay. This is a gamma limit.
Okay.
So for you, I will think of having a device, so you have actual boundary conditions, which you can impose those.
Okay.
So on the U is illusion.
For B, there is a boundary condition.
So sorry. What is U?
U is U is for brittle.
Oh no, okay. Then you have no boundary conditions
boundary
because you fracture at the boundary. Of course, if you have fracture at the boundary, then you pay the fracture. Okay. So the conditions are only on the substrate. Okay. So if you go the form of the substrate, you can have periodicity conditions.
Thank you. Thank you. That is another.
I hope that my question is not too much naive, but okay, I'm just thinking about the deformation of metal substrates which are induced by the temperature cycles, and then you have patina on top that can be more or less homogeneous, and cracks are making big differences in the protectiveness of the patina, and the same, of course, also for the layers like incrolat and so on, which have a different thermal behavior as they can make cracks. This kind of description, you think that could be applied also to try to model, to investigate this kind of behavior in which you have a substrate and some layer, but with different mechanism where you can describe the thermal behavior or mechanical properties.
Thermal behavior. In principle, yes, it is flexible.
Okay. Thank you.
and from the online people, if there are no questions. Okay. Thank you very much for this. The second one is Roberto Busonera from the University of Sassari. Please.
No, ma fa, metti già sotto schermo. Se vuoi se il microfono, se no no.
Ma penso che mi si senta.
Adesso la faccio.
Ma non è per me, niente di significativo. Nascondita. Ok. Okay, good morning. Let me introduce myself just with a little reference. Yesterday, Paola Lettardi said that we cannot know everything, and this is exactly the mood that I use today, because I'm not an expert of mathematical modeling. I am a researcher or ancient topography archaeology in the field of archaeology at the University of Sassari. So today I will not present any experimentation of mathematical modeling, but I will try to propose or suggest some point of view that could be useful for about the potential of mathematical modeling in the restoration of and protection of cultural heritage. Starting from few more suggestions coming from Ferguson and Filippo Giuliani, that in the study, you said in the study of cultural heritage, we should study, first of all, the process of construction of a building or of a structure, not only what we have nowadays. And in this process, we have to know why a structure or a building was built in a particular way. Here you see the plan of Temple of Minerva Medica, the original plan on the left and the last plan on the right. On the right, of course, there are a lot of of intervention that are statical intervention to let the temple, the building could be more functional for the necessity of that time. Even because nowadays expert who face with the historical architectural problem on historical building usually used to make a lot of relief, different relief, one for architectural type, one of material, one of the decay. All of them are different from each other, and all of them are usually taken as one part, one lonely part, and there is not a whole approach of the building. So my first recommendation, my first suggestion could be to think about the analysis of a building, of a historical structure as a whole body that could be studied in one only approach. This is the main goal that usually is searched for cultural heritage. So the creation of atlas of material, atlas of masonry composition or mortars composition, and this is usually taken as the point of arrival of each study. So not study the structure, the process of the structure, but just maybe study the state of a building as well I can see nowadays today. Again, the idea of that historical building are usually studied as surface, as a sum of surface. So just through two dimension and not as a building usually should be studied. So 3 dimension, 4 dimension, but just as a sum of surfaces. What could be useful? First of all, a kind Cairoli Giuliani call this type of research as a crack map. Please be good with my graphic on the right, but we know that the damage of a building usually starts from at the moment it starts to be used. Material start to have damage at the moment that the building of a structure or a structure start to be used. And along the story of the building, usually come a lot of events that can increase the damage or can increase the healthy of the building. To have a global idea of this situation, the crack pattern, a crack map, could be useful to understand how to intervene on this kind of situation. First of all, trying to understand different and discontinuity of the foundation soils. So a study of the soils, to study the load connected to the structures, the geometry of the building, and the variety of load, accidentally load, permanent load, then affect the structure. And of course, the event that can be occur as earthquake, landslides, or sudden event that can increase the health of a building. I guess that in the 5 stages that are commonly used for the fact-finding, for the study of historical building, a common fact-finding process, 3 of them could be useful even for mathematical modeling. First of all, for a survey made by a comprehensive autoptic and verification on site. So a map of lesion, a map of the damage of the building that could be helped by mathematical modeling. An identification of the edification process, an analysis of a structural change, And at the end, the model, the 3D model of the representative, the representation of the building that could be helped by the summary of the survey and the technical research made for this kind of research. This is a kind of the event that I was mentioning. This is a part of the Aurelian walls along Porta Pia that was attacked during the battle on Porta Pia, and this event caused, of course, damage to the wall, and we don't know exactly, but we can imagine that the entire structure of this sector of the wall are still today have still today a damage that maybe are increasing along the time. So this is the first stage, a first step that could be taken into account. Again, the reconstruction of part of a building. There is the relief of a church in Sardinia, and you see here the difference of the pattern of the wall. On the right side, there is, of course, a reconstruction of the building, and a kind of research in this field should be understood why this kind of reconstruction was necessary and why this kind of reconstruction was made. And again, a use of different materials that could be useful on one end, but could be increase the damage on the other side. Here, even yesterday, we saw an image from Peltuinum, a Roman site close to L'Aquila. Here is a zoom analysis on the part of the wall of the ancient theater, and here the restoration process in order to keep the process of conservation of the perimeter wall of the theater was used this new material on the ancient one, and of course here we can imagine that the surfaces between the two materials can be collaborate or not. It should be something to study, to understand, and to understand the process of this kind of collaboration. Even because the study of the masonry could be really difficult along the process of the technology. This graphical, this sketch show how a masonry, the capacity of resistance of masonry can change in order to different materials that can be used, and this happens usually when the wall is made by opus cementitium, by different material that should collaborate and that are different kind of behavior. And a study at the same time, the study of mortars that can be used have different capacity of resistance. So even in this situation, the mortars, the resistance of mortar should be studied in order to understand the type of load that have to that has. That's why a few years ago I collaborate with a project of research in Sardinia, mother project that was made to understand the behavior of some structures in Roman cities, ancient Roman cities, and you see here a kind of atlas of the mortar used from a wall of the ancient bath of the Roman city. this kind of study, on one hand, I said before, could be not enough to understand the behavior of structure, but on the other hand, could be useful as well to understand the type of material used in ancient walls, and at the same time to prepare maybe some experimentation of the capacity of that wall, of that material, maybe even in a non-invasive way. So trying to find this kind of material not inside the wall, but in the cave or where this material were found. Another point of view is on once again on the process of construction is about some consideration of the phases that can interest a building. Here is an example that comes from some the research of Alessandra Ten, who is a professor here in Rome at Sassari University, about their phases of building of Aurelian wall. Here you see on the left the Aureliano phase, on the right the Honorio phase, who duplicate the wall in some part of this path, and of course studying the kind of structure. You see here and on the other image a kind of fracture that came into the wall. This is of course came because of the new structure, the load of new structure on the ancient one. And in this case, I guess that the mathematical modeling could be useful to understand the process of this kind of damage, to understand in time and in a kind of measure how this damage can involve, if it will involve or not. You see here other example, even in this case on the Aurelian wall, that can understand the ancient, to understand the process of ancient structure. Remembering one last thing, that for the case of Aureliano walls, we are talking about one monument that is long 18 kilometers along Rome. So even the condition of soil, even the condition of material, even the condition of the exposition of agent that could be dangerous for the structure have to be taken into account to understand how it's possible to study the structure, and in the future what kind of intervention could be useful for the monument. So not only take into account, pay attention to a part of the monument, must trying to pay attention to all the whole monument that could be protected, that should be protected. So one more opportunity. In conclusion, I trying to describe before the process of the damage in a structure, in a historical, in ancient structure, trying to understand from a near zero the damage start until 2021, passing through events that increase the damage. Could be useful. I try to propose another point of view in which mathematical modeling should be useful from an inverse path. So not just to understand how the damage could be increased in the future, but for people who work in cultural heritage in the field of archaeology, trying to understand how the damage started. So try to understand how the damage from 2021 to year zero try to pass to the past and not just to the future. Thank you.
Are there some questions, remarks? I have the one. So if you can explain better this inversion of time.
And starting from a point of view, starting from past, I try to understand that the damage of a structure usually starts at the beginning of function of the structure. I don't know if it could be possible try to invert this point of view. So we have a state today in 2021, and maybe through a mathematical modeling try to go to the past, maybe to try to understand not just what can happen in the future, but try to understand how this state of damage occurred or came. So passing from event 2 and the cause made by the event 1 and so on. Yeah.
Thank you.
You're welcome.
Are there other questions online?
No, the remark is the following. I'm very surprised that you consider the building as a collection of surface, mathematics as a manifold, because then you use solid mechanics. And I don't know, I'm a little bit confusing about
because in the field of cultural heritage, I try to explain at the beginning of my speech. One of the main goals is to create an atlas of material, but not only of material, even to technical of construction and edification. So we try often to understand the texture of a wall, and rarely we study the complexity of static and of the structure. That's why I said that mathematical modeling could be useful to open this point of view, not only to the study of surface and to the creation of this kind of atlas, but even to understand, as you told, the complexity of the solid, the complexity of the entire body of the building.
I think that this idea to go back in the past is not feasible really, because you know, these kind of processes are in general diffusing. So if you take essentially an equation, you can go forward, and you cannot go backward because it is imposed. I mean, if you go forward in time, you have just one solution. But only this, yesterday we seen a lot of models of possible damage, there are other models. But usually these models have a time direction. And so usually the inverse process to go back in time is important. I mean, you have a lot of possibilities. So you have not a unique way because time the pass off. I mean, in principle, it's not feasible at all.
This is just an example that I try to draw to explain this kind of situation. It's sure that all the events in the history of a building are made for one vision. So trying to check the path of the damage in a structure to understand maybe why an integration of a part of the building came necessary or not, I think could be useful to understand the history and the process of building. Honestly,
May I have this? I think that the situation is similar to the. I found some similarities with the experience in restoration, for example, of bronzes and so on, where you just look at your structure and you find some pattern, and from that pattern you can guess what's happening before.
Yeah.
In this way, to do this, you have to have some kind of maps, some kind of model in which you know that if you start from this point and then happens this one, this one, this one, this one, then I will get this one. So I think that the matching between your mathematical idea and your architectural idea is that to some extent you need some modeling of what's happened in the right time direction. And then you need max or final events that you can check with your structure and making some kind of pattern recognition. Would it be possible? Just a guess.
No, I think that mathematical is very important. I mean,
I don't know.
there is a one way.
From my point of view, my field of research is trying to understand why something happened in the past.
Yeah.
So trying to understand this architectural field, I would like to understand maybe if some intervention in a structure should be or wasn't necessary because of static reason or not. For example, the intervention of Honorio in Aureliano walls was made necessary because of barbarian, because a stranger were coming in Rome, of course. So he told to build a taller wall to protect the city, but this occurred in a damage in the original structure. So we already know this, but for new structure, I think could be useful. I don't know. Honestly, I don't know if in a mathematical way could be a real way to approach to the monument. But I think could be useful trying to understand not only the damage it could go in the future, but in some way trying to find the right parameters, trying to understand even if we can understand how this damage go back to the origin and understand the reason because it was created.
Okay. Maybe with some constraints, with some supplementary information,
yeah,
you can try to do something. But I think there are a lot of ways to destroy a monument. And so, I mean, you can come, but
there is not only one line.
Yeah, there are the same final situation from many different
parameters.
Yes, I heard that it is possible to invert the height and the depth in a Gothic situation. If you can suppose that there is much different between the orange.
Of course, there is not only line we should be taken into account a lot of parameters. Of course, this is just suggested.
Yes, from the mathematical point of view, if the events are not so terrible disaster, but there are only fluctuation, you can think to invert it. Very interesting. Thank you. Okay. The next speaker is Barbara De Filippo. Good morning. Okay. So, good morning. I would like to start with a consideration. During my PhD course, I collaborated with Roberto Busonera in the elaboration of a mathematical models for copper corrosion. My background is in chemical fields, so I think that it's a really interesting experience to try to put together mathematician aspect with the chemical one. And I remember that I did a lot, tons and tons of analysis. And I remember that speaking with Roberto, she sometimes told me, yes, but I don't need all this kind of analysis. I just need these little parameters. And sometimes I say, okay, now what can I do? Because it's not easy to try to match two fields that are similar but really far from that are really far. So today I would like to speak about shape memory alloys. My presentation will focus the attention on corrosion processes, on the application of this kind of shape memory alloys, corrosion processes, and I will give you just few details about the mathematical model that we are trying to elaborate. So this is an ongoing project between the Institute of Applied Math and the National Research Council of Italy, the Department of Chemical Engineering at the University of Sapienza, and the University of Milan Sapienza with Professor Elena Bonetti. Okay. No. Okay. I'm sorry. So, shape memory alloys are really, so smart materials are really a really peculiar class of materials because they are able to recover their initial shape through a thermoelastic transformation. In particular, we have two main aspects, the shape memory aspect and the superelasticity aspect. The shape memory effect is the effect according to which the smart alloys are able to return to their original shape after being heated or cooled. The second one, the superelasticity effect, is the ability to undergo large deformation and to immediately return to their original shape upon removal of a load. We can see we have many different types of SMA alloys. The most important are the nitinol alloys. Then I will show you the different applications. We have also iron alloy, but today I would like to speak about copper alloys, in particular copper zinc aluminum alloy. Okay. Here I would like to show you the austenite martensite. Okay, the austenite martensite transformation curves. In the possibility to recover the initial shape is due to the austenite martensite transformation. The austenite is a stable phase at high temperature, and the martensite is a stable phase at lower temperature. And here we reported the percentage of austenite and martensite according to specific range of temperature. A certain hysteresis, so the possibility to have austenite and martensite both, it's possible at some specific range of temperature. Okay, the martensite transformation. So the transformation from austenite to martensite is diffusion vessel. So we don't have a chemical bond breaking, but we have a little movement of the atoms that allow the transformation from austenite to martensite. In particular, the transformation
it's divided into two main phases. The first phase is the base phase, in which we have the formation of this new martensite. And the martensite has a really flexible structure. The second step of this transformation is the lattice invariant shear, where we have a rotation of the chemical bonds without any breaking of the bonds, and also we have this particular twinning martensite that is a structure that allows to shift, so to come back to austenite 1. So it's a movement between the two different fields. And here, I would like to show you the final arrangement that we have. So this arrangement allows us to come back to austenite and then to return to martensite several times. Okay, here just I would like to show you few SMA applications. Nitinol are really so can use also for in aerospace domain. Here we have the use of nitinol for the feet alignment or other biomedical application. Here I would like to show you the use of SMA spring, the SMA spring, and many other different applications. Okay. A really interesting application is the self-expandable stent. Stent is a nitinol, is made up of a nitinol SMA, and it's a really interesting device because it is contracted in a martensite field. It is put inside the artery, and thanks to the body temperature, we have an enlargement of this metallic mesh that guarantees the body flat. The enlargement is due to the austenite, so the austenite formation. So we can see the differences between the movement between austenite and martensite. Here again, we have some civil engineer application of copper, zinc, aluminum alloys. And I don't know if you can see, there are some reinforcement elements that can be used for civil structure, building, bridges. And this kind of SMA alloy are really cheap. So they are interesting from economic point of view. Okay, briefly, we identified corrosion processes using different chemical solutions. We set up the opportune laboratory corrosion condition, and then we evaluate the physical and chemical parameters. We try to evaluate if the chemical variation affect the shape memory effect and or the superelasticity effect. Okay. From chemical point of view, we would like to investigate the resistance of this kind of alloy to corrosion. For doing this, we used electrochemical analysis, in particular potential dynamic polarization curves, and we analyzed the tarnish product developed on the surface using two really well-known techniques. Scanning electron microscopy with an X-ray microanalysis in order to detect and to analyze the metal morphology, and the XRD diffraction for the microstructure analysis, for the crystallographic identification of our samples. Okay, so we focus our attention on copper, zinc, aluminum alloy with 20% of zinc and 5% of aluminum. We produced this alloy in the laboratory at the Department of Chemical Engineering, thanks to the support of Engineer Brozzo and Professor Natali. And we cast our bronze ingot at 1150 centigrade. Then we cool the ingot at 25 Celsius degree, and then we analyze it. It was really important for us to try to simplify our research and to have a beta phase brass. The beta brass is the phase that guarantees the shape memory aspect. So here we have the copper zinc phase diagram, according to which we selected the opportune composition, and then we analyzed with an XRD instrument the surface of our samples. This image is it's really interesting because here we can see the grain of our alloy. The grain is characteristic, and here we have the interface between the grain that are important to analyze because it's a preferential site for corrosion, because we can consider it as a defect. So it's an interface where we have high energy. So the corrosion process are really activated. It's a preferential site. Few images, a few photos regarding the instrument used for casting alloys. Here we have a centrifugal injection oven. We use these molds for producing the ingot. I'm sorry, but it's not possible to see. But this ingot is very shiny. It looks like gold. Obviously, it's not gold because it's copper, zinc, and aluminum. But it's really, really shining. Let me say that it's really beautiful. And here we have a cutting off machine in order to section these ingots and to have the samples that can be used for the experimentation. Okay, briefly for the electrochemical analysis. Here is our samples. This is a classical configuration for electrochemical potential dynamic polarization. And we used different corrosion tests with different tests. Nitric acid with a different molarity, because it's well represented acid rain in urban context. Also, we used sulfur acid with different concentration, because it's represents very well acid rain in industrial context. And then we use a solution that reproduced seawater. So we would like to see the differences in corrosion, the corrosion process regarding different chemical atmosphere. Okay, here we have the sample after the first potential dynamic test in nitric acid. I would like to show you this SEM observation. This is a chemical image where the different gray levels respect the composition. It's not a photo. And here we have the characteristic formation of the twin martensite. So the movement that I described before, it's well represented here, because it's really characteristic. The structure of martensite is really characteristic. Here we have the curves obtain different concentration of nitric acid, and here it's reported the current densities as function of potential applied. For a better understanding of the entire process, we characterize with the EDS spectrum, and here we have the peaks, the characteristic of the element of our samples. Okay, this is the specimen after a sulfur acid test. Here again, we have some observation of the martensite forms. Obviously, in this case, we have a product mainly copper sulfate because we use a sulfuric acid. And also again, the current density with respect to a different concentration, 0.01 molar, 0.1 molar, and 1 molar. And then again, the EDS spectrum of corroded surface. The last one is the use of a synthetic seawater. I would like to show you this characteristic of corrosion pit. A corrosion pit is a localized corrosion phenomenon that generates a hole, and it's really, really dangerous because it can activate many other corrosion processes starting from this part. In particular, the galvanic corrosion, electrical corrosion, and so on. The EDS spectrum shows that we have mainly not that is a common product due to the chlorine. Here I would like to show you some corrosion morphologies before and after test with different etching of the surface. In fact, the surface can be pickled with a different kind of acid in order to show better the structure before, in order to have, from metallurgical point of view, a better understanding. Finally, we try to compare shape memory alloys with the super elastic alloy. The first two spectra, they are XRD spectra. So it's a spectra that gives information about crystallographic structure of the samples. And here we have the as cast, so before any treatment, and the second one is after heating treatment. So it's possible to see that the austenite, the peaks of austenite are well oriented. In the second, these are two spectra are related to a cast alloy with a memory shape form. And here we have an improvement of the XRD thanks to the thermal treating, because it's really, really important to operate with the samples easier. Because if we have a different kind of pieces, we will also have different kind of corrosion process that generate a sort of difficulty, in particular if you want to model it. What I can say is that when we decided to model a phenomenon, we need to simplify the chemical aspects, but at the same time not to lose important details. So it's a balance between what exactly we can put into the models and what is the information that I can have from the data. So it's important that the simplified information that we can use in the model describe very well the overall process. Okay, here just one of the last slides. I will show you the corrosion behavior of the previous alloys, and here we calculated the corrosion rate respect to the different alloys before and after treatment in order to see the kinetics of the process. Regarding the modeling, so in our group, we collaborated also with Professor Elena Bonetti. Professor Elena Bonetti developed in past a shape memory models. I think that it was a Fremont model. It's called Fremont models, and it's a phase transition models in which they take into account the transformation of austenite into martensite and vice versa. They consider the difference in the structure because the austenite is a cubic cell. The martensite is a tetragonal cell. So this change in the cell permit to have a shape memory left. In our model, we will start from these models, and we would like to have corrosion parameters. The final aim is to understand how the corrosion affects the shape memory. In our samples, we cannot see any affection of the shape memory. So the shape memory is with our test is guaranteed. But it's important to understand how the corrosion can affect the shape memory, because these are elements that have a civil that are used for civil protection for so the application are really wide. So important to better analyze the effect of corrosion in structural activities. One part that is missing for us is to evaluate stress strain test. So to put our sample under stress strain test in corrosive environment under XRD analysis, because it's important to have a characteristic to better understand the behavior of our alloys in particular condition. They also at the same time to perform XRD, because the stress strain causes a variation in the peaks of austenite and martensite, in the ratio between the peaks of austenite and martensite, and it's really interesting to consider into our future. So, thank you for the attention. Questions and comments from the online? No? Okay, thank you very much. Yes.
Yeah.